Today's video, I will be going over the reverse chain rule. So I've got here the integral of 2x over x squared plus 1. So we can use the reverse chain rule to integrate this. So what exactly is the reverse chain rule? When can we use it and how can we use it? So in this red text box here, I've got k times f prime x over f of x. So what does this mean? So f of x is our denominator. So if we assign f of x to our denominator in this integral, which is x squared plus 1, well, if we were to differentiate this, the derivative of x squared plus 1 is 2x. And what do we know here? Well, it's actually written in the form shown in this box here, where f prime x, the derivative, is actually our numerator, and f of x is on the denominator. So if the derivative of the denominator is on the numerator, you can use the reverse chain rule. So what I'm going to do is I'm going to block out this 2x. Just pretend it's not there for the moment. Now I want you to replace this 2x, which I just blocked out, with a 1. Okay? And now I just want you to integrate that for a second. So we know if we tried to integrate x squared plus 1, well, it would be something like ln x squared plus 1 if we had to take a guess. Okay, fair enough. So what we'll do now is we'll try and differentiate ln x squared plus 1. And I'm going to get rid of this box because we can now not ignore it. So let's try and differentiate ln x squared plus 1. And this is where the chain rule part of the reverse chain rule comes in. So we can now use the chain rule to differentiate it. So if we were to use the chain rule, we'll set w equal to x squared plus 1. That will essentially become y equals ln w. Okay, so let's differentiate both sides. We'll get dw is equal to 2x and dy is equal to 1 over w. Okay, so let's put all of this together. So we'll get dy by dx. So dy by dx is equal to 2x over w, which is x squared plus 1. Now, if you have been observant, look at our dy by dx. It's 2x over x squared plus 1. What else is 2x over x squared plus 1? Look at our integrand here. I'm just going to get rid of that one there. Our integrand is 2x over x squared plus 1. So, therefore, what we can say is that the integral of 2x over x squared plus 1 is this. Look, it's ln x squared plus 1 plus c. And hopefully that makes a little bit more sense. We'll have a look at another example and hopefully you'll better understand it. Okay, so I've got another example here. It's cosec over 3 plus 2 sine x. Well, what we do is we ignore the cosecs. So I'm just going to cross it out and pretend it doesn't exist. We'll replace it with a 1 for now. And what we do is we integrate 1 over 3 plus 2 sine x. And that will roughly give us ln 3 plus 2 sine x. Okay, so now all we need to do is differentiate it. We know, using the chain rule, that w equals 3 plus 2 sine x. And if we were to replace y with w, we'll get y equals ln w. Okay, so let's differentiate both sides. We'll get 2 cos x here, and then we'll get 1 over w here. And then putting it all together, so we'll get 2 cos x over w, which is 3 plus 2 sine x. So that tells us dy by dx. Okay, so let's compare dy by dx with our integrand. So our integrand, now we can include the cos. So we know that dy by dx, if you look at it here, it's actually exactly double our integrand. Because our integrand is cosec over 3 plus 2 sine x. Look at dy by dx, 2 cosec over 3 plus 2 sine x. So therefore, if we divided both sides of this equation here by 2, well, we would get a half dy by dx is equal to cosec over 3 plus 2 sine x. And we know that cosec over 3 plus 2 sine x is the same as our integrand. So what we can say is that the integral of cosec over 3 plus 2 sine x is equal to a half of this here, our y. Ln 3 plus 2 sine x plus c. And that is our answer. So let's take a look at another example. So what's the first thing that we do? Well, we ignore the sine x cos x and we just pretend that there is a 1 there. So let's integrate 1 over cos 2x plus 3 and we will get ln cos 2x add 3. There we go. And then let's use the chain rule to differentiate this. So let's set a variable w equal to cos 2x plus 3. And if we were to rewrite our y expression, we will get y equals ln w. Okay, so let's differentiate both sides, shall we? So we'll get minus 2 sine 2x. And then y prime will be 1 over w. Putting all of this together, we'll get minus 2 sine 2x over, and then we know w is equal to cos 2x plus 3. So that is dy by dx. Now for our next step, as you know, we compare this dy by dx to our integrand. So let's now ignore this and we can reintroduce our sin x cos x on the numerator. Well, it's sort of similar. Well, the denominator is cos 2x plus 3 on both the integrand and the dy by dx. But look at our numerator, it's not really similar. Well, we can do something about that. And we know from trigonometry that sine 2x is equal to 2 sine x cos x. Okay, so what we can do is replace this sine 2x with this here. So let's quickly do that. So I've quickly replaced the sine 2x with this here. Okay, and now we'll quickly expand the brackets. So minus 2 times 2 will just be minus 4. And we'll essentially get minus 4 sine x cos x. Okay, now we can come back to our integrand and compare. Well, on the integrand, on the numerator, we've got sine x cos x. Okay, well, dy by dx, we've actually got minus 4 sine x cos x. So therefore, dy by dx is actually minus 4 times larger than the integrand. If we divided both sides by minus 4 on this equation here, well, dy by dx would equal our integrand. So what we can say is that the integral is equal to minus 1 over 4, and then it'll be y, which is ln cos 2x plus 3. And of course, plus c. So we're going to look at some other examples. So let's move on. Okay, so I've got the next example on here. Now it is a bit different because it's no longer a fraction. So can we use the reverse chain rule still? Well, yes. And as you can see in this red box, it also works if the function is written as kf prime x, f of x to the power of n. Okay, so I will quickly explain what that means. So f of x to the power of m, in this case, so this f of x here, is equal to sine x. And the n is equal to 2, because obviously sine squared. So what is the derivative of sine? It's cos. So we can say that f prime x is equal to cos x, and then k here would be 3. So we can still use it. And yes, the derivative of sine squared x isn't just going to be cos. It's probably going to be something like 2 sine x cos x or something like that. But we can still use it here. What we do in this example is we take a function y, and what we do, we assign it to either the cos x or the sine squared x. But what we do, we increase the power by 1. So as you know, with integration, you increase the power by 1 each time. Whereas with differentiation, you times the power by the coefficient, then you reduce the power by 1. So what we'll do is we'll take sine squared x, but instead of taking it as squared, we'll take it as cubed. So as you can see here, I've actually increased the power of sine by 1. So let's use the chain rule now. So if we set a variable w equal to sine x, and we rearrange our y equation, that'll be w cubed. If we differentiate both sides, we will get cos x. Here we will get 3w squared. And just putting it all together, we will get 3 cos x sine squared x. That will essentially tell us dy by dx. Well, if we compare dy by dx, which is 3 cos x sine squared x, with our integrand, dy by dx and our integrand, which is 3 cos x sine squared x, they're actually both the same. So we can say the integral of 3 cos x sine squared x is equal to sine cubed x. So here it would be sine cubed x plus c. And there we go. So here I've got another question. And what we do is we take either the cos 3x or the sine to the 5 3x. I'm going to take the sine to the 5 3x, and I would recommend that you do so. I would also recommend what you would do is try it with cos 3x, see where it goes, and it probably will not work, I'll tell you that. So I've taken sine to the 5 3x, and I've increased the power by 1. We've got sine to the 6 3x. Okay, so let's use the chain rule. So we'll get w is equal to sine 3x. And we know if we rewrite y, we get w to the power of 6. W prime would be 3 cos 3x. And y prime would be 6w to the power of 5. And if you put them together in the chain rule, we would get 18 cos 3x, and then times it by w to the power of 5, sine to the 5 3x, and that tells us dy by dx. So hopefully you can sort of see why we chose the sine term rather than the cos term. Because when we differentiate sine to the power of 6, we actually get very close to our integrand here. Whereas if we did it with the cos 3x, we probably wouldn't get close, because obviously we wouldn't have this sine to the power of 5 3x. We will be nowhere near. So now what we do is we compare dy by dx with the integrand, where we know that dy by dx is 18 times larger than the integrand. So what can we say here? The integral, well, if we divided dy by dx by 18, we'll get cos 3x times sine to the 5 3x, which would then give us the same as our integrand. So therefore we can say 1 over 18, and then we take y, which is sine to the 6, 3x plus c, and that will give us our answer. Okay, so for the final question today, we've got the integral of cosec squared 2x times cot 2x dx. Now there is something that I just want you to consider, which is the derivative of cot. The derivative of cot would give us minus cosec squared x. So I want you to consider that and then think about which one you would choose. So hopefully you would choose the cot 2x. So we increase the power of cot to get cot squared 2x. And let's differentiate it using the chain rule. So we know w is equal to cot 2x. And if we were to rewrite y in terms of w, we'll get w squared. Differentiating both sides, dy would be 2w. And w prime would give us, well, we know the derivative of cot is minus cosec squared. So therefore, the derivative of cot 2x would be minus 2. I'm probably not going to fit it all in here. But we'll use CSC. That is another way of shortening cosec, by the way, CSC. Cosec squared 2x. Okay, so let's put this all together. So we'll get, 2 times 2 is obviously 4. So we'll get minus 4w is equal to cot 2x. And then we'll get cosec. Now finally I have enough space to write it fully this time. 2x. Okay, and that tells us dy by dx. And then let's compare it to our integrand. Well, it's actually similar. Now, I just want to point out, you can also do the same with cosec as well. The derivative of cosec is minus cosec x cot x. So you can actually use cosec squared in this case. But in other questions, you may not get so lucky. I'll put it that way. So let's compare dy by dx with our integrand. And we know that dy by dx is minus 4 times larger than our integrand. So if we divided dy by dx by minus 4, we would get the same as our integrand. So therefore, we can say that I is equal to minus 1 over 4, and then y is cot squared 2x. So cot squared 2x plus c. And that is our answer. So that's all for today's video, guys. Hopefully this topic makes a little bit more sense. Leave a like if you enjoyed it, and I'll see you in the next one.